Okay. So in the third section of chapter 16, we will consider residue integration method. It's an important application of the previous discussion in this chapter. All right, so first of all, we'll consider a complex function f of z, which has a pole or an isolated essential singularity at the point z equal to z sub 0. And then we let q of z n from 1 to infinity and c minus n, c minus z0 to the nth power. Okay, so we let this one be the principal part of f of z at z equal to 0. Now we let gamma be a closed path in the complex plane such that this singularity z sub 0 is not in gamma star. Okay. All right. So the situation is here, and okay. So this is gamma. So here is gamma star here. Okay, now gamma t minus z0, this distant function, okay, is continuous on the compact okay. Let's see here. Since the distance function z minus z0 is continuous on the compact i.e. Closed and bounded set gamma star. As we have discussed in chapter 14, okay, so this function, it has a minimum value, say D1, which must be greater than 0, and a maximum value D2, okay. Okay, so that's the range of the cross path gamma is contained in the closed annulus D bar Z0 1 2 whenever R1 is greater than 0, but less than equal to D1, less than equal to D2, and less than equal to R2. Okay, so we will see the situation. So that this is, say this is D1, D1 here, okay, and this is D2, right, and we find so this is R1, and this is R2. Okay, so you can see that. Okay, so you can see gamma star is contained, the whole gamma star is contained in the closed annulus with inner radius R1, outer radius R2. Whenever R1 is less than equal to D1 and R2 is greater than equal to D2. Okay, so we have the situation here. Now, we know the principal part. Now, the principal part is a Lorentz series. Okay. with which has the convergent, so which has the convergence open annulus, A, z sub 0, 0, and infinity. Okay? Since since 0 x an isolated singularity. And alpha equal to lim sup equal to 0. Okay? All right, so here this is 1 over alpha is infinity. And it's single isolated annulity means that the beta should be equal to 0. Okay, as we discussed before. So we have this one. All right. So now, and by theorem 16.1.c, okay, this Lorentz series, okay, converges uniformly, okay, in the closed annulus A bar Z0 R1 R2. Okay, and this implies converges uniformly in gamma star, because gamma star is contained in this closed annulus. Okay, so this. All right, and so by theorem, by the 15.5.3, we have 2 per I. So if we do the integration of the principal part over the closed path gamma, okay, so this one is gamma summation and from 1 to infinity z minus n, z minus z0 to the nth power, and dz, okay? All right, and because that, this series converges uniformly on gamma star. All right, so we can exchange the infinite sum and the integration, the line integral, okay? So we have summation n from 1 to infinity, and and the C minus N, so this is constant, times 1 over 2 pi I gamma 1 divided by Z minus Z0 to the nth power of dz. Put dz here. So we have, all right, so this is from the uniform convergence property stated in theorem 15.5.3. So we have that. Now by the definition, okay, so by definition of index function, I and D with respect to gamma, and by the remark 14.2.1 in chapter 14. So we have that 2 pi I gamma 1 over Z minus Z0 dz. Right? This is actually the index of at Z sub 0. Okay, so this is the function of gamma with respect to this cross path gamma at the point Z sub 0. And also, as we know in the remark, all right, we know that this line integral actually is 0 for all n greater than or equal to 2. Okay, so we know if n is greater than or 2, we have evaluated that. Okay, so we have, all right, so that's the integral gamma, the line integral of the principal part over a cross path, okay, over a cross path here, okay, such that over any cross path, such Z, the singularity Z sub, the isolated singularity Z sub 0 is not in the range of gamma. So that this line integral becomes C minus 1 and becomes the index gamma of at Z sub 0. Okay? So that we have this equation. Okay, and we call this 16.1.3.1. Now, assume that the complex function f of z, right, is analytic in a punctured open disk. Okay, D prime with the center Z0 and radius R. Right, so the center is Z sub 0. Okay, so we suppose that because that the Z sub 0 is an isolated singularity, so we always be able to find, okay, such a punctured open disk, so that f of z is analytic. Okay. So now in the spatial case, okay, that gamma is a simple closed path in D prime, okay, of Z0 R. Okay, so suppose gamma is a simple closed path, okay, in the punctured open disk, which enclosed Z sub 0 and is oriented counterclockwise. Okay, in this case, then we have that 1 over 2 pi I. So the line integral okay is equal to C minus 1, and this one is by theorem 16.1.1, because in this theorem that if a function is analytical in an open annulus, so a punctured open disk is a special kind of open annulus. Okay, so that this is a special kind of open annulus, then it will have a Lorentz series expansion, and the coefficient Cn, okay, the Cn especially C minus. So we know, okay, that so that is analytic in this one. So this implies by theorem 16.1.1 that f of z has a Lorentz series expansion, and with the coefficient, which is 2 pi I, okay, of f of z and z minus z0 n plus 1 and dz. Okay, so the Cn is this one. For any simple closed path gamma in the open annulus. Okay, so this is from theorem 16.1.1. Okay, and when n is minus 1, then this is just equal to this one. Okay, so this is with n equal to minus 1. So when n equal to minus 1, C minus 1 is equal to 1 over 2 pi I, and the line integral of f of z over the closed path, the simple closed path gamma. Okay, so simple closed path. So we need a simple and closed path. Okay, so this is from theorem 16.1.1. But because the index, because gamma is simple. Gamma is simple, and which is enclosed z sub 0, and oriented counterclockwise. So the index function with respect to gamma at z sub 0 is equal to 1. Okay, and so from here you can see. So this is 2 pi I of the over the principal part. Very interesting. You can see. So you can see that we have this identity. So we say this is 2 here. Okay. Okay, and so the identity, as you can see, this is when the gamma is a simple. It is important that it's a simple cross path. Okay, in the punctured open disk. All right, so we have that. This formula, this identity is good for any cross path gamma. All right, and the gamma star does not contain z sub 0. Okay, so this is more general. Okay, so that a simple, right? But in here, this gamma says this is just a closed path with this sub 0, not in gamma star. All right, so they apply to different kind of cross path. All right. Now the number C minus 1, all right, is called the residue of the function f at the point z equal to z sub 0, and we'll denote as here C minus 1 will be denoted as the residue at z equal to z0 of f of z. Okay. And we also note that C minus 1 is also the residue, okay, of the principal part. Q z of f of z at the point z equal to z0. Okay. So how to find the residue of a complex function f at an isolated singular point z equal to z0. Okay. All right, and the following we will derive a couple of formula for poles of finite orders. Okay. All right, so now suppose that f of z has a pole of mth order, okay, at z equals 0, then f of z is representable by a Lorentz series about z equal to z0. Okay, so f of z is equal to n from minus m to infinity and Cn. So, okay, and so that with C minus m, which is not equal to 0, okay, because it's a pole of m's order. So C minus m is not equal to 0. And so we can take out a factor okay, and z minus z0 to the nth power. Okay, so with c minus m not equal to 0. Okay, then if we multiply m of z, f of z by this power term, okay, we find that this is summation okay. Bn z minus z0 and okay with Bn equal to Cn minus m, and we see that B0 is equal to C, which is not equal to 0. Okay. All right. So this one, this has become to a power series, so that this one has a removable, isolated singularity at z equal to z0. Okay. And then this function is analytic, okay, at z sub z0. Okay, so we turn by multiplying the f of z with this power function, then you get a power series. So you see z sub 0 becomes to be removable, okay, and so this function is analytic at z equal to z0, okay. And because that if we want to find the the residue. So we know residue C minus n, C minus 1. Okay, and C minus 1 is actually B n minus 1. Okay, because here, so when n is equal to m minus 1, when n is equal to m minus 1, this is C minus 1, and so n is m minus 1. Okay, and this one is equal to, so by the pilot series expansion, and of the okay. All right, so this function, you take the m minus 1's derivative divided by m minus 1's factorial and evaluate it at z equal to z0. Okay. Okay. So this is from by theorem 15.4.8. Okay. Okay. So this is the formula to have the residue. Okay. At a pole of m's order at z sub 0. Okay. Okay, so now the residue of f of z at a pole z sub 0 of m's order is here. One over m minus 1's factorial, and the limit, and the z goes to z0 of the m minus 1's derivative. Okay. Now, in particular, for a simple pole, which means that m equal 1, so we have the residue is equal to, so m equal 1, okay, so this is equal to limit, z goes to z0, and z minus z0 times f of z. Okay? So this is to find the residue, okay, for a simple pole at z sub z0, then you take the limit of this product, okay, for z goes to z sub 0. All right, and furthermore, if f of z is the ratio p of z and Q of Z. And both P of Z and Q of Z analytic at Z sub Z0 and P of Z sub 0 not equal to 0. So the numerator is non-zero at Z equal to Z0 and Q of Z having a simple 0 at Z equal to Z0. Okay. Okay, so the denominator has a 0, simple 0 at Z sub Z0. Right, so because now when we take reciprocal of Q of Z, then this simple 0 becomes simple pole. Okay. Okay, so then QZ X here, and from 1 to infinity, Qn Z sub 0, n factorial, Z minus Z0 to the nth power. Okay. Okay. And with Q prime of Z0 not equal to 0, because Z sub 0 is a simple pole, right? So the first derivative of Q, okay, is non-zero at Z equal to Z0. Okay, so we have this one. And so in this case, so that the residue of Z equal to Z0 and F of Z has a simple pole at Z sub Z0, so we have simple rho, so we can use this formula. So the residue of equal to the limit Z goes to Z0, Z F of Z. Okay, and so that this is limit Z goes to Z0, P of Z, and so you will see that we will have summation and from 1 to infinity Q n 0 n factorial and Z minus Z0 n minus 1. Okay? Because you multiply with Z minus Z0 here, so that it will reduce by 1. All right. And now, because this is a continuous function, and we know that when Z goes to Z0, the numerator goes to, so this is the limit. And this is the limit, because the denominator Okay, that the numerator is P of Z0 because P is continuous. And when Z goes to Z0, we have the constant term. So this is equal to Q prime Q1 of Z0. Okay. Okay, so we have this formula. Okay. So this is a very special case and quite useful. Okay. So now we have find a couple of formula to compute the residue, right, of a function at a pole of m's order. Okay. Now we want to, because the formula here, the formula is good for simple cross paths. Okay, so we want to generalize that. All right, so to generalize the identity in the formula 2, right? We observe that if a complex function f of z has a pole over an isolated essential singularity at at the point z sub 0, and if q z this one is the principal part of f of z at the point z sub 0, then the complex function g of z, which is f of z minus q of z. Okay, so this complex function has a removable isolated singularity at the point g sub 0, and is analytic at the point z sub 0. Okay, so this is a very important observation. All right. So this is a way, all right, to render an isolated singular point to be removable. Okay, to be removable. We just subtract the principal part from the original complex function f of z. And so this is a good point, because now we can generalize. So in general, we can remove, okay, a finite number of isolated singularities at z equal to z1, z2, dot, 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 up to zn, okay, simultaneously. Okay, by subtracting their principal parts. Q1 Z, Q2 Z, dot, 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 up to Q1 Z. From f of z, okay, so that the complex function so now the complex function g of z, which is f of z minus q1z by q2z, q1z, right, has removable isolated singularities at z equals z1, z2 up to z sub n. All right, and is analytic at each of these points. Okay, so this is become to be analytic at each of these points. All right, so now, so we can state the first theorem. So this is the residue theorem. Okay, for simple closed path, all right, in a simply connected domain. All right, so f of z is analytic, okay, in a simply connected domain, okay, except for a finite number of points. Okay, so except for a finite number of points, z1, z2 up to zn, in D, at which Fz has poles over isolated essential singularities. Okay, so F is such a function. So it's analytical in a simply connected domain D, except a finite number of points. Okay, and at this point, the complex function of Z has poles or isolated essential singularity. All right, and gamma is a simple closed path. Okay, in D, but say minus Z1, Z2 up to Zn. All right, so minus the isolated singularities. Yeah. So which means that this isolated singularities will not be on gamma star. Okay. Right, so it's simple, and which encloses, okay, so which encloses the isolated singular point Z1, Z2 up to Zn. And is oriented counterclockwise. All right, then we have that. Then we have the line integral of f of z, right? So the line integral of f of z over the simple cross path gamma. This line integral is actually equal to 2 pi I summation of k from 1 to n of the ratio at z equal to z sub k of f of z. Okay. So you can see that this line integral, right, can be evaluated if we know the ratio of the complex function f of z at each isolated singular point. Okay, here. Okay, so let's see a proof. Right. Now, so we let Q I Z be the principal part, okay, of f of z at z equal to z sub I. Now for I from 1 to n. Okay, and then we let g of z to be f of z minus the sum of these principal parts. Okay, then g of z, as we discussed before, g of z is analytic in D. Okay. Right. So g of z is analytic in D, and right. And so by Cauchy's integral theorem, in a simply connected domain, which is just the theorem 14.2.1. So we have that the line integral of g of z over a simple cross path gamma will be 0. Okay, because gamma is a simple cross path. Okay, and so which implies that is equal to the summation okay, is equal to this one. But this is 2 pi I summation I from 1 to n of the index of gamma of g sub k and the residue z equal to zk of q z sub I and qiz. Okay. This is from the formula. Okay, here. It's from here. Right. So Q is this one. Okay. So this is by 16.3.1. Okay, so we have that. But we know this equal to 1 since gamma is simple. Okay, so the index is equal to 1. Okay, and so finally we have 2 pi I summation. Okay, I from 1, okay, to n, and the residue z equal to zi and f of z. Okay, since the residue of z is equal to the residue okay, the ratio of the principal part of z of the point at z sub I. Okay, so we have that before. When we talk about the ratio, yeah, here. So the ratio of f at the isolated singularity z sub 0 is the same as the ratio of the principal, okay, of f of z at that singular point. Okay, so that we complete the proof. Okay, so the evaluation here. All right, so let's take an example. The function now is z and exponential pi z divided by the first part of z minus 16 plus z exponential of pi of z. Okay. And we can see that for this ratio, the numerator, this numerator is an entire function. Okay. And the denominator is also an entire function with 4 simple zeros, okay, with 4 simple zeros there, okay, and the 4 simple zeros because that that would be so this is 2 pi I and 4 times k. All right. So and k 0, 1, 2, 3. Okay. So the pole, so there's, okay. Okay, so f of z, so you can see that this function has 4 simple poles. at z equal to plus minus 2 and plus minus 2i. And 1 here. And the 1 isolated essential singularity at z equal to 0, which is from here. Okay, so this one has the isolated essential singularity at z equal to 0 here. Okay. Now we consider we need a bigger picture here. Okay, so this function has 4 simple poles, and we select a simple cross path. Okay, so this is this ellipse. This ellipse we orient it this way, counterclockwise. Okay. So this is our gamma star. All right, and so if this one is analytic, so the simply connect domain is the C, right? Except at what? Except at z equal to I and 0. Okay. Just here. So we have except 5 points. Okay. Right, and that has 4 simple poles at it and 1 isolated essential singularity. Okay. Now, now we let gamma be a simple closed path, okay, with gamma star, which is the ellipse x squared plus y divided by 3 square equal to 1. So it's this one, okay? And oriented counterclockwise. All right, so now then we have here gamma of f of z. Okay, so that's gamma of z, e pi z, and z4 minus 16 dz plus gamma. So we have, okay, so this is the isolated essential singularity, gamma and z, e pi over z and dz. Okay. Now, there are only 3 singular points inside or enclosed by gamma star. Okay, so you can see that. And plus minus 2 are outside. Okay, so that okay, so these two single points are irrelevant. Okay, so now we compute. So we compute okay. Now, oh, by the way, I'm sorry, because we need in this the theorem, we need a simply connect domain, right? And that the function is analytic in the simply connect domain, except for a finite number of points. So we cannot select. So we select D, which is not C. Okay. Okay, in C, right? Except this one. And so we should find a simply connect domain. And a proper choice would be, this choice is that all right, so D, okay, D here. So D, there is a simply connected domain. Okay, this is connected domain. All right, and f of z is analytic in D, except. All right, except at z equal to plus minus 2i and 0. Okay, so that in D, f of z has 3 isolated single points, 1, 2, 3. Okay, and this is 3 single points is enclosed by this oval. Okay, so you see that. Okay. Because we need to use theorem 16.3.1. Okay. We cannot use the whole complex plane as the simply connect domain. Why? Because that f of z has more single points, plus minus 2. Okay. Okay, so gamma okay, so note that by selecting D to B such that okay, so the real part of the Z is between not 1, sorry. So this is minus 1 over 2. This is 3. This is minus 3.5. 3.5 minus 3. Okay. All right, so that we restrict ourselves. So this D is, okay, as the D, which is simply, simply connected domain. And contains gamma star. Okay. Also, and f of z has 3 isolated. So f of z is analytic, okay, in D except it's z equal to plus minus 2i and 0. Okay, so we have that. Okay, and the line integral here, we have that. So now we compute the residue. We compute. So we compute the residue. Compute residue of f of z at z equal to plus minus 2i. Okay, because they are, so these are simple poles. Okay, and the simple poles can be computed. So the residue z equal to 2i of z e pi z z4 minus 16. Okay. And so we use the second formula. Okay, so this is this one. Okay. And so this limit goes to 2i. All right, and oh, by the way, sorry. Now, the derivative of the denominator is 4 times, so it's 4 times z cubed. and this is z e pi z, z equal to 2I. All right, and this is 1 minus 16. Okay, and the residue of z equal to minus 2I, z e pi z, the fourth power of z minus 16. So this is the z e pi z for z cube, z equal to minus 2I. And again, this is 1 minus 1 over 16. Right. And to find the residue at an isolated essential singularity, then you have to find Lorentz series expansion. Okay, so now since z e pi over z is equal to z, and so that this is the exponential function has the expansion, okay, pi over z, nth power, and factorial. Okay. All right. So that's so we have that z plus pi square to factorial z plus pi cubic 3 factorial z2. Okay, and so we focus this term. All right. So we have the residue z equal to 0 of z e pi over z is equal to pi square divided by 2 factorial. All right, so this is pi square divided by 2. Okay, and then the line integral becomes 2 pi I of minus 1/16 minus 1/16 plus pi square divided by 2. So this is equal to pi square minus 1/4 and I. Okay. So this is the evaluation of line integral over this simple cos pars gamma. Okay. So we have that one. Okay. So the job becomes much more easier, okay, by residue. Okay, as we see that this theorem is actually is an extension of the identity we have in equation 16.2.1. Okay, so so now the goal, we want to extend. So the goal, right, of the rests of this section is to generalize the identity in equation 16.3.2 to a meromorphic function f of z on an open set omega with A the set of all poles of f of z in the open set omega, and to a cycle gamma in A in omega minus A such that the index function with respect to the cycle gamma, right, is 0 for all z not in the open set. Okay, so this extension, because if you look at the theorem here, in this formula, we require that this complex function, all right, is analytic in a simply connected domain, except a finite number of points, right? So that we consider simply connected domain. Okay, and also the cross path should be simple. Okay, it's simple in this simply connected domain, and not in its range not pass through this single points. Okay. So our generalization will be that that the simply connected domain can be generalized to the open set, any open set. Okay, can be any open set. But the singularities in this open set, the f of z has only poles. We can't have isolated essential singularities. Okay, we can't, because that we deal with the meromorphic functions. Okay, so for meromorphic functions, that we only have pole sets. Okay, so that, but the requirements for gamma to be simple can be generalized to cycle, arbitrary cycle. Okay, so this is a big, a big generalization, right? So that, okay, but one requirement needed, because we need to apply the global Cauchy's theorem, so that the index function with respect to the cycle gamma, okay, with cycle gamma, all right, should be 0, okay, for all the points outside the open set omega. This is, you will see this is required, okay, by the global Cauchy's theorem. Okay. Okay, and now we need a result before we state our main theorem. All right, so omega is an open set in the complex plane. Okay. And A is a subset of omega which has no limit points in the open set omega. Okay. And the gamma is a cycle in omega minus the set A, such that the index function with respect to the cycle gamma is 0 for all z outside of the open set. Okay? Then the B set, right, which just points in the set A, such the index with respect the index function with respect to the cycle gamma is non-zero. Okay. Now this set is a finite set. Okay, this is a finite subset of A. Okay, so that the index function. And and a detailed proof is given in the lecture notes. So I'll ask you to read the proof there. Okay. So I want you to keep in mind that if we select a subset A of the open set, such that this set A has no limit point in the omega. Of course, the set A may have a limit point outside omega, but that is our concern. We concern that that A has no limit points in the open set. Okay, and if the cycle, all right, in omega minus A, such that the index function, okay, is 0 for all z. Oh, not. I'm sorry, not in open set. Okay, so in that case, then that we collect all points such in A such that the index function has non-zero value. Then this collection of points we call the B set. It is a finite set. Okay. All right. So that We note that as discussed in the remark, in a remark in section 6.2, okay, after, I think that would be after the definition of meromorphic function, okay, a subset A of an open set omega which has no limit point, has no limit points in omega, consists of isolated points in omega. Okay? Because A has no limit point, right, in omega. So every point in A is an isolated point. Okay. All right, so we state the residue theorem, okay, for cycles in an open set. Okay, all right, so omega, all right, it's an open set in the complex plane. Okay. A is a subset of omega, right, which has no limit point in omega. F is a function which is analytic in omega minus A, okay, and has having an isolated singularity at each point of A. All right. So that F can be a meromorphic function or more, because the set A, the set are not just only the pole set. The set A may include isolated essential singularity. Okay, all right. So this theorem is more general than what I said before. Okay, it's more general than that because the A set may include isolated essential singular points. Okay, right. So this is more general, and gamma is a cycle. Okay, in omega minus A, such that the index function with respect to gamma is 0 for all points not in the open set. Okay, and then the conclusion is that the line integral of the complex function f of z over the cycle gamma can be computed to be 2 pi I summation of A in capital A and the index of gamma of A and the residue z equal to A of f of z. And as we will see in the previous theorem, that in the A set, okay, then there are only a finite number of points in A such that this index is non-zero. So this becomes to be A in B and index. So actually, this is a finite sum because the A set may be an infinite number of set, an infinite set, sorry. Okay, so gamma, oh, by the way, the cycle gamma here. Okay, so that this is the theorem we have. Okay. All right, so let's see the proof. So by theorem 6.3.8, the sum is indeed a finite sum. Where B is, this is set, okay, so I have to say All right. So now, if B is the empty set, now we let the G of Z to be F of Z. Okay. So originally, we just stated that. Now, if B is not empty set, so, and it's finite, so we let A1, A2, up to AN be all the points in B, right? And B has a finite number of points, as we have shown in theorem 16.3.8. All right, and we let Q, I, Z be the principal parts of F at Z equal to A1, at AI, for I from 1 to N. Okay. And also we let, in this case, then we let GZ to be F of Z minus summation I from 1 to N of QI Z. Okay, so we define that. Okay, so if B is empty set, which means that for every point in set A, the index function with respect to the cycle gamma, all the point in A would be 0, so the B set is an empty set. In this case, we let GZ defined to be F of Z. But if the B set is non-empty and has M point here, then the GZ would be the difference of FZ and the sum of the principal parts of these points in B. Okay. Okay, then G of Z, okay, has removable isolated singularity singularities at Z equal to A1, A2 up to AN. Okay. Of course, if B is an empty set, then that F of Z has no removable isolated singularity, right? Because there's no points. Now we let omega 0 to be omega minus A minus B. Okay, so that this one, and which is an open, which is an open set. Okay, since the set, this set, has no limit point in omega. Okay, so as discussed in the remark after the definition of monomorphic function in section 16.2. Okay. So now we know that this omega 0 is also an open set. Okay? So now G of Z, right, is an analytic function on omega 0 on the open set omega 0, and gamma and the gamma is a cycle So gamma is a cycle in omega 0 because gamma is a cycle in omega minus A, and the omega 0 is bigger than omega minus A. So of course that the cycle gamma is in omega 0. All right, now, so by the definition, okay, of the set B, the index function and D with respect to gamma is 0, right, at every point of A minus B, so that the index function would be 0 for all Z not in omega 0. Okay? So let's see. All right. And this is omega. All right. And so we have some points, say here. So this is the point, the prime. And it's in A by B here. Okay, so let's see here. This is much more, it's in omega 0 complement. Okay. But omega 0 is actually so this is equal to omega complement union of A, B. Okay? Because omega is this one. So if you see that, so this is omega complement. And so this is omega complement union B. Okay? This one. If you say omega intersect complement and complement, right? And by De Morgan's law, this is omega complement union complement. So this is omega complement union of, okay? If you use the De Morgan's law. All right, so you have this, okay? And we know that our assumptions saying that the index function is 0 for all z are not in omega, which means that for all z in the omega complement, okay? And for every point in this set, the index function is also 0. Okay, so that we know the index function is 0 for all z in the complement of omega 0. Okay, so now by the global Cauchy theorem, so now we can apply the global Cauchy theorem. So we have that the line integral of gz over the cycle gamma is equal to 0. Okay, so this is one of the conclusions of the global Cauchy theorem. And so this implies that f of z dz is equal to, because of the difference, is equal to the summation of I from k from 1 to n gamma qk z dz. And this is equal to 2 pi I summation k from 1 to infinity index function of gamma of ak and residue of z equal to z equal to ak of qk z. Okay. Okay, and so this is by 16.3.1, the formula layer. Okay, because the equations in 16.3.1 that the cross can be any cross path. Okay, so that it can generalize to any cycle. Okay, so we have that, and this is the residue we have. Okay. Okay, and the residue of the principal parts of the complex function f of z at the point a sub k give us the residue of the function itself at the same point. So that is index of gamma of ak here, and the residue of z equal to ak and f of z. Okay, so we have that. Why? So this is a very general theorem, okay, for any cycle and in an open state. All right, so now we will apply the residue integration method for the integration of real integrals. All right, so we consider the real integral of the type. So we want to evaluate. And the integrand is a function of cosine theta and sine theta, okay, and d theta. And the theta is from 0 to 2 pi. Okay. All right, so suppose we want to evaluate this point where f of xy, all right, it's a real rational function of x and y. Okay. For example, that f of xy can be y squared and 5 minus 4x here. Okay, so it's a real rational function, which means that it's a ratio of two real polynomial function. Okay. All right, and so we assume that f of xy. So if we assume that if we consider this as a function of cosine theta and sine theta, all right, it's finite for all theta in between 0 and 2 pi. Okay. All right, and we observe that cosine theta, by definition, is EI theta plus E minus I theta divided by 2. Okay, and the sine theta, XE I theta minus E to the minus I theta divided by 2I. Okay. Now, we will think about EI theta. So this is a complex number And we know when theta is from 0 to 2 pi, so that this is actually run over the unit circle, right? Okay, so this is theta here, and this point, this is the EI theta. Okay, and this is the complex plane. Okay, so we know that, so we may think about that. This is z plus z minus and 2, and here is z minus z inverse 2i. Okay, so we have this. All right, and with z equal to EI theta. Okay. All right, and 2 pi. So now the integrand, we can establish a complex function. So now we let f of z to be f of z plus z minus z to the minus 1, 2, z minus z minus 1. Okay. And because f itself is a rational function of the two arguments, so that this has become to a rational function of complex value of z. Okay, it's a rational function. All right. So now since dz, because this, right? So we did z equal to EI theta. So dz is equal to I EI theta, d theta. So IE, the d theta is equal to dz Iz here. Okay, so we go to there. We have the j itself is the gamma with the line integral of f of z and dz Iz. Okay, so that you can see where gamma is the unit circle. Okay, in the complex plane, and the oriented counterclockwise. Okay, so you can see the real integral here. This is the real integral. Becomes to, okay, becomes to that, this one. Okay. If you think this is too quick, maybe I will do it this way. So, 2 pi, okay, and f now is E I theta plus E I theta 2 okay, and d theta here, okay. this is from there. And we establish that the gamma from to C, okay, and theta goes to EI theta, okay. So this is what we have. Okay. Okay, so this is what we have that, and all right, so that the gamma theta is equal to EI theta. Okay, and this implies gamma prime theta is equal to I EI theta. Okay, so that 0 and the F okay. Now, so we have 1 over IEI theta times IEI theta, this theta here. Okay, and so this is 0 to 2 pi F theta, and this is gamma prime theta, okay, gamma prime theta, and the day theta, okay, with the so that we can replace this is by gamma theta, and gamma theta plus gamma theta inverse divided 2 gamma theta minus gamma theta minus 1 2i. Okay, so this is the line integral. So you can see, so over the gamma and the function of z plus z minus 2, z minus z 2i, and 1 of I of z, and the dz. Okay, because here, this is dz. Okay, and so that this is gamma, and f of z, and times iz and dz. Okay, by our definition, this f of z here. Okay, so we turn the real integral into a complex line integral here. So you see that over the unit circle, and this unit circle is a simple cross path there. All right, so Let's see an example. Suppose we want to evaluate 1 over square root 2 minus cosine theta and d theta here. Okay? So we know the f of xy is equal to 1 over square root 2 minus x here. Okay? And so f of z, which is f of z plus z minus, and z minus z inverse 2i. And so this is 1 over square root 2 minus 2z plus z inverse. Okay. All right, this is fz. So that fz and iz here becomes minus 2i and times 1 z square minus 2 square root 2z plus 1. Okay. And we can factorize this one. So this is z minus square root 2 plus 1 and z minus square root minus 1. Okay, so the function, so the kernel, the integrand you see that has two simple poles. Okay. All right, and so now, okay, this is the unit circle. All right, and this is 1 minus 1. Okay, and we have a point here. So this is square root plus 1 and minus 1. Okay, so now the J is equal to the unit circle Fz Iz dz. Okay. All right, and this is 2 pi I. So we have okay, and we know that the A set, so from here A consists of 2 points, and the B set X points such that the index with respect to the unit circle non-zero. And we know because for this point, it is outside of the gamma, so the index is 0. Okay, so we know the index of gamma of this point is 0. But the index of gamma, which is equal to 1. Okay, so the B set consists only this point. Okay, and this is the point, and so we know from the theorem, this theorem. Okay, from this theorem we know that. We just take the residue here, All right. So that this is the A in B, and index of gamma of A and residue Z equal to A F Z. Okay, by our set. And so this is because we have only one point, which is square root 2 minus 1. And the index at that point is equal to 1. Okay, this is 1. So that this is equal to residue of Z equal to square root of 2 minus 1 and of Fz here. Oh, Fz divided by Iz. Okay. Okay. And it has a single point of that. So that we see that by the first formula we have, or we can use so we know this is 2 pi I residue Z equal to by the way, this is equal to this one, residue of minus 2 I and 1 plus 1. Okay? Okay, and this cancel. All right, and so we have minus 4 pi, okay, and the residue for this one, we will do it 1, and we take the derivative of that. So this is 2z minus 2 square root of 2, evaluate z equal to minus 1. Okay? Okay, and this is becomes 2 pi. Okay, this is equal to 2 pi. All right, so for this example, this integral is equal to 2 pi here. Now consider an improper real integral. Okay, and we can think about that. The limit go to here plus the limit beta goes to positive infinity. Okay, extended to two sides. Where f of x is a real valued function on the whole real line. Okay? Now, if both limit exists, we may couple the two independent passage. All right, two passages to minus infinity and the plus infinities, and the right not equal to the limit r goes to infinity f of x dx. And this limit is called the Cauchy principal value. Okay, of the integral. Written as so that this is saying that the principal value of this improper integral. Okay, so if this, because the passage to minus infinity and the passage to plus infinity are independent, so you evaluate this improper integral independent of this one. Okay, so if both limits exist, of course, then the improper integral in the left-hand side exists. In that case, then we can couple these two independent passages into just one passage. All right. So this is a little bit has a symmetry, right? You can see here, and this evaluation, this limit is called the Cauchy principal value, okay, of the improper integral. We have to make a point. The Cauchy principal value may exist even the two limits. So just say this is 16.4.1. So this is 16.4.2. Okay, if the two limits in 16.4.1 do not. Okay, so let's take an example to see that. The Cauchy principal value of this integral, okay, by definition, okay, but because x is an odd function, so we know that this is 0. So the Cauchy's principal value of this improper line integral is 0, so it exists. But if you compute, all right, this quantity, you know that this is positive infinity. Okay, this is positive infinity, so it does not exist. And limit give us minus infinity. Okay, so these two limits does not exist because this is not finite. Okay. Now, so to evaluate the Cauchy principal value of an improper integral, right, like this one. We will consider okay, a complex line integral over a simple closed path. Okay, gamma. All right, so let me write down. So this is R. So this is a complex plane. This is minus R. Okay, and we go. Okay, so that gamma is that so we have the x star, okay, and the x is from 0 to pi to c, such that for every every t sent to R EIT. Okay. So the point here, the point is R EIT. Okay, the points here. So X is a path. Okay, so R is that from minus R to R, top plus the S here. Okay, so it's go this way from the point minus R, go to the point positive R, and then turn over there. So this is the half circle. Okay, so this is the upper half circle, okay, or half circle with center 0 and radius big R. All right, so you have that. Okay. All right, and so this gamma is a simple cross path here. Okay, so now we by of a complex function f of z by replacing the real variable x in the function of x with the complex variable z. Okay, so originally we have f of x. Okay, we have f of x, right? And so we replace the real variable x by the complex variable z. Then to construct a complex function, oh, I forgot the word of a complex function f of z by, okay, so that's, all right, so we will we will consider a complex line integral over a simple cross path. So this path is here, already be here, okay, and of a complex function f of z, okay, so that okay, so that all right, you have z here, and because the gamma is the dot sum of these two paths, so we know this is equal to from minus r to r, f of z and dz, okay, plus the x here, f of z and dz, okay. And this integral, because the line, the curve, okay, that is from so you can see, for example, to C, so that's T x is RT. Okay. Oh, maybe I will say that. So that T will goes to T. Yeah. T this goes to t, so that the derivative, so that this is equal to 1. Okay. And so this is actually the integral f of x dx. Okay. So you can see I use x, go to x, and so the equal to 1. All right, so this line integral over this segment, okay, it's just the original, the real integral from minus r to r, okay. And for here, because x is here, so the xt prime is going to be equal to I r e I t. Okay, so this is I r e I t here. Okay, so this is from 0 to pi, okay, and f of z is r e I t, okay, and times I r e I t and dt. Okay. So this is z is here. Okay, now, so now this integral becomes to gamma f of z and dz, okay, minus EIT and times IR EIT dt. Okay, and so the Cauchy principal value of the improper real integral becomes to the limit r goes to infinity of, okay, so this is the limit of r goes to infinity of the line integral minus the limit pi of r dt. Okay, so this is the limit here. Now we make assumption, okay, for this one, okay. Assume that f of r EIT, right? So the absolute value is then equal to alpha of r divided by r, okay, for all t from 0 to pi. Okay? Suppose that. i.e., f of z has the magnitude less than or equal to for all z in the S star. Okay. All right, and with the limit as r goes to infinity, alpha of r, this function equal to 0. Okay. So we assume that the magnitude of this function, okay, can be upper bounded by a function of r when the point is on the upper circle, okay, in the upper half circle with radius big R. Okay, so in this case, then so by this assumption, then we know that the limit r goes to infinity of this integral. Okay, so now, so that we know that f of r EIT, okay, and IR EIT. Right, so the integrand, we look at this integrand. The integrand has a magnitude, all right, has magnitude less than or equal to alpha r, okay, for all 0 in t in pi. Okay, okay, so the whole integrand, okay, is an upper bound. So this implies that the limit goes to the infinity, okay, of the f value. Okay, is less than or equal to the limit r goes to infinity, 0 to pi, and f of r EIT IR EIT absolute dt. And so this is r goes to infinity of alpha r, and this is equal to 0. Okay. So under the assumption, then this limit is 0. Okay. All right, so this limit is 0, and so now the principal value of now becomes to be of f of z and dz. Okay, it's here. But we look at that when r going bigger and bigger, okay, when r going bigger and bigger, then we will see that that it will cover, then it will cover the upper half plane. Okay? So this becomes to be 2 pi I times the summation of all in A of the residue A in A, okay, and Z equal to A of Z, such that the imaginary part of A is greater than 0. Okay? So they will include the poles. Okay? You may have some so that all the isolated by assuming that fx has no singularity in the real line. Okay? There's no singularity in the real line. And the set, okay, A of isolated singular points has no limit point. Say that in the complex plane. Say that. Because we want to apply theorem 16.3.b. Okay. Okay. Now, in particular, So example. Okay, f of x is equal to p of x and the q of x. Okay, it's a real rational function. It's a real rational function. Okay, where px and qx are polynomials of real coefficients such that q of x is not equal to 0 for all x in R. Okay, so this makes sure that if we replace the real variable x by the complex variable z, then the complex function f of z will have no singularity. Okay, so this is important. Right, so this one implies that f of z defined to be p of z and q of z, okay, has no singularity in the real line. Okay? Right? Because when z is a real number, then the denominator is never 0. Okay? So this is well defined. All right, so we require this one. And also we require the degree of q of x. The degree of the denominator is greater than or equal to the degree of the numerator plus 2. Okay. And this implies that the magnitude of f of z, okay, so this is equal to p of z, q of z. Okay, now so that this would less than equal to m of z square for all z is equal to r greater than or equal to r0. Okay, so this is implies that if we think this is too quick, then well, we will see here. So the p, suppose p has the degree is a m, okay, zm plus a0, and this is a n Cn plus Bn up to B0 here. Okay. Okay, and here Am not equal to 0, Bn not equal to 0, and n is greater than or equal to m plus 2. Because the degree of Q is greater than or equal to the degree of P plus 2. All right. Okay, so now we have Z, M, and this is the Zn. Okay, so, all right, and we have times, that's AM plus AM minus 1, Z, okay, A0 minus M, and this is Bn, okay, Bn plus Bn minus 1, Z minus 1, plus plus B0, Z minus N here. When N is very big, as you can see, that so you can see that, so we can have AM plus AM minus 1. Oh, no, by the way, sorry about that. Okay, so right, so this one would upper bound by number, all right, for all Z, okay, greater than or equal to R0. All right, so if the magnitude of Z is big enough, then we know we can, given an M, we can find an R0 such that this is true. Okay, and so this implies that f of Z, okay, is less than or equal to 1 over Z minus M times M for all Z is big enough. Okay, and this is this square. Okay, for all so we have this magnitude, and so that will be less than or equal to M of R square for all Z in S star. Okay, because that the magnitude of Z on the X star X R, just R only. Okay. All right, and so that this is equal to R alpha r with alpha r is equal to m divided by r. So which is going to 0 as r goes to infinity. Okay. So the degree of the denominator is that greater than or equal to the degree of the numerator plus 2 implies that this assumption implies that this assumption is true. Okay, this assumption is true here. Okay, so this is true, and so that this integral goes to 0 as r goes to infinity. Okay, so we have okay, and now the set A of isolated single point has no limit point. Why? Well, you know that this is a complex polynomial, and the complex polynomial has a finite number of root. Okay, so that the set of isolated singularity of f of z, okay, is a finite set, and any finite set has no limit point, of course. Okay, so that all right, and we know so that any single point of f of z must be a root of q of z, root of, okay, so that A is a finite set. And has no limit point in C. Okay. All right. So the principal value of the integral of px, qx, dx, okay? X equal to 2 pi I, and the summation a to a, and residue f px of qx here, and the imaginary part of a should be greater than 0. Okay. Oh, sorry. PZ, QZ, I'm sorry. Okay. Okay, so the principal value can be evaluated by the residue calculation here. Okay. Okay, a more specific example can be done. All right, so this is the example that if this integrand is a real rational function, like this is very common to occur, and so to evaluate the principal values, then this is in term becomes to the evaluation of the residue, okay, of this rational function. Okay. And that you should have to sum over all the points in the set of isolated single points, but with the imaginary part which is positive, which means that the point is located in the upper half plane of the complex plane. Okay, so that is the situation here. Okay, all right, and application of this is about to evaluate the Fourier transform. All right, so Fourier transform. And its inverse transform. Okay, so we know that for complex value functions, the Fourier transform is defined to be f of x e minus I xx dx, okay, for all x in R. Right, so this is the Fourier transform of f of x, okay, and the inverse Fourier transform x under a certain condition that the original function can be obtained in the way okay. Under certain conditions discussed in chapter 11. Okay, so we know that we have this one. Okay, if f of x has the discontinuities, then this part may be the average, all right, of the right limit and the left limit at every point. Okay. Okay. So and you can see that the evaluation here, the evaluation involving the improper integral. Okay, involving the improper integral there. So we will assume okay, so we will provide so the assumption here is that that f of x, f of z, okay, they have the magnitude. Maybe I assumptions. Okay, 1. Okay, the f of z has the magnitude less than equal to alpha r divided by r for all z in star or in maybe I will, okay, for all z in the circle, all right, with center 0 and radius r. Okay, so in the whole circle, okay, with center 0 and radius r. And the second requirement will be the f of z of and E okay. So let g of z be either f of x, f of z or f hat of z. Okay. Because we are considering these two, so that we use g here. Okay, because we have two formula here. Okay, so g of z may be f of z or f hat of z. Okay, but and the g of z is here. And the second thing is that that g of z and the e of I as e of ix z. Okay, this one okay, or like let's see, g of z has okay, has no singularity. Okay, has no singularity in the real line. Okay, and the third is no singularity in the real line, and third, the set A of isolated single point of g of z, okay, has no limit point. In the complex plane. All right, so we require these three conditions. Okay. Okay. Because that we make several conditions here. Okay. So for example, this one. Okay. So this is corresponding to the first one. And GZ has no singularity because we cannot have the singularity in the real line. And the set A of isolated single point has no limit point. Okay? There's no limit point. So that we can apply theorem 16.3.b. Okay. All right, and in this case, then okay, then the integral, for example, the f of x, okay, and e minus I x x dx. So this is f of x in here becomes 2 pi I. Okay, so this is become 2. I will write down, okay, 2 pi I, and summation of A to A and f of z, e minus I s z here. Oh, residue, forgot. Z equal to A of the fz e minus x xz. And z is in A also. Minus, so okay, so that imaginary of A, which would be less than 0, and 2 pi I summation A in A. Okay, residue z equal to A, f of z, ISZ, and the imaginary part of greater than 0. Okay, if x is greater than 0, and if x is less than or equal to 0. Okay. So it depends on the x, right? If x is non-negative, then we select all the isolated single point such that it's located in the lower half plane, right? But if this is true, then we have that. Okay, so this is for the Fourier transform. Okay, and for the so if we want to evaluate the inverse Fourier transform, EI XX ds. Okay, then this is becomes 2 pi I summation of A in A, and the imaginary part of A is positive raised to z equal to A xz if x is greater than or equal to 0, and the 2 pi I in A, imaginary part is 0 raised to if x is less than or equal to 0. Okay. Okay, so we have these two evaluations. Okay. And the last one, so it's good. All right, now, so you see all the improper integral have the assumption that the integrand has no singularity in the real line. But what if we have singularity in the real line? Okay. All right, so consider definite integral here, and where the limit x goes to A, the magnitude going up, okay, for some A is in the alternate interval. Okay, so the situation is that so the evaluation. So how do we do that? And this one will be considered right? So we may evaluate, because that we have singularity at little a. Okay. All right. So provided that the two limit exists. Okay. Now we consider the Cauchy principal value of this integral is defined as epsilon goes to 0 of the a minus epsilon from capital A plus a plus epsilon b. Okay. Right. So if these two limits exist, then Cauchy principal value must exist. But conversely, if the Cauchy principal value exists, then these two limits may not exist. Okay, so that so note that limit and limit exists implies that the principal value exists, but the direction may not exist, right? So we have only one direction. And the example, you can see an example that the principal value of x, the third power. So when you evaluate this one, and we know that it has singularity when x equals 0. Okay, and we know that the limit epsilon going to 0 minus epsilon minus 1 plus okay, this is limit. So it is 0. Okay, so the Cauchy principal value is 0, so it exists, but it cannot imply this. But if you integrate, you know that the limit okay, so that this is minus infinity, and okay, so this one is also infinity. Okay. So to evaluate the principal value, all right, of this integral, such that the integrand has a singularity, all right, in between A and B. Okay. All right. So now we need a theorem from the textbook about the simple pole. So if on the real line, okay, the simple pole. All right, so if f of z has a simple pole at z equal to a on the real axis, then so we look at the situation. So A is here, so this is a simple pole, and this point is A plus R. This point is A minus R, and we do the half circle in this way, and this is called the C2. Okay, so C2 star, and the C2 is a path, okay, from 0 to pi goes to z, such that for every t we have A plus R E I T. Okay, so the C2 is the path. Okay, and its parameterization is from T to A plus R E I T here, and T is just from 0 to pi, so it will go through just the upper half circle. Okay, then if we evaluate the line integral of f of z dz, okay, and remember that as we have a pole, okay, it's A here, and which is simple, all right, okay, and we let the R goes to 0, right? So when the R goes to 0, this is approaching to the pole A. And this limit exists, which is equal to pi I and times the residue of the function f of z at z A. Okay? So we have such a line integral here. And the proof is simple. Okay. Now, so since f of z has a simple pole, okay, at z equal to a, the Lorentz series expansion of f of z about z equal to a is here, is f of z equal to c minus 1 and z minus a, okay, plus g of z. Okay, and the g of z, this one, which is analytic, okay, at z equal to a. Okay. And the c minus 1 is just the residue of f of z at the point A. Okay, so we have this data here. Now, and we know the C2 is so that so now the GZ, okay, so we know that GZ, okay, is a continuous function. Okay, so because GZ, so GZ is continuous. Okay. So GZ is, because GZ X analytic at Z equal to A, so GZ is continuous. Okay, so it's a continuous function on the cross disk, center is A, and with some R. Okay, R0, so we'll say R0. Okay, for some R0 greater than 0. Okay, but we know this is a compact set. Since the cross disk is closed and bounded, so it's compact. Okay, so now, so since X closed and bounded, okay, there exists an M greater than 0 such that the G of Z itself is upper bounded by M for all Z in the cross disk. Okay, so it's in the cross disk there. Okay, so it's bound. It has some bounded. Okay, now, so C2 of f of z dz is equal to that C2, so equal to the line integral over C2 of the first term, this one, so C minus 1, and Z minus A, and the dz plus C2 and G of Z and dz. Okay? dz here. Now we look at this one, C2GZ dz. So the magnitude is this equal to C2 and GZ and dz here. Okay. All right, and this is less than equal to M, C2 and dz. So this is the arc length of C2. But the arc length of C2 is equal to pi r and times m. Okay, because the arc length of a whole circle is 2 pi r, right? And so half circle would be pi r here. Okay. Okay. Now, how about the first integrand? But C2, C minus 1, and the Z minus A, dz. Okay. So we will do the substitution. So by the metrization, this is from 0 to pi, C minus 1, and this is the C2 T minus A. Okay, and dz will be the C2 prime T and the dt. Okay, but so the C2 prime T is equal to I R E I T. Okay, and the C2 of T is A, so that this is equal to C minus 1 and R E I T. Okay, because C2 T is A plus EIT. So C2 prime T is equal to IREIT. Okay, so we do that. This is the IREIT and DT. And so we cancel this one. So this is become true. C minus 1 times pi I. Okay. Okay. So we have this one. So it's a constant. So this term is a constant here. Okay. All right. So that the limit as r goes to 0 of C2, Fz and dz becomes 2 pi I times C minus 1, okay, plus the limit of r goes to 0 and C2 gz dz. Okay, but because the magnitude is less than this one, so this implies that the limit as r goes to 0 of this line integral, okay, less than equal to limit pi rm, which is 0. Okay, so that this is 0. Okay, and so this is our result, pi I in here, and C minus 1 is just the residue of the fz function at the point d to a. Okay, so we have this result. Okay, so it depends on the residue we have. Okay, so now we consider the case that A equal to minus infinity, B is equal to infinity. Okay, and so we want to find the principal value, and f of x has simple poles. Has a simple poles at so that f of x has a simple poles on the real axis. Okay. Right, so fx has simple pole on the real axis. Okay, and we with that we assume that the set A of isolated singular points of f of z, of f of z x is a finite set. Okay. Now the principal value of the so this is equal to so we will see here, the single point, so we may have say A1, A2, A3, maybe we have that, and say that, so this is 0 here. All right, and say we would do so this is the A1 plus epsilon, A1 minus epsilon, A2 plus epsilon, A2 minus epsilon, and here is A3 minus epsilon, A3 plus epsilon, etc. And we take minus R here and R here. So we have that big half circle. So now go this way. Okay. All right, so this, and this is the x, right? So x star with x send 0 pi to C, and t goes to R, E, I, T. Okay. So this is the up circle here. All right, and so we have now if R is big enough, okay, so if R is big enough, then the gamma becomes to be minus R, say, and A1 minus epsilon, that, and we have so in this direction we have C1, in this direction C2. Okay, maybe we up to AN. So okay, maybe AN. So this go to minus C1. Okay, because with this C1 oriented counterclockwise. Okay, so this is minus C1. Okay, and that from A1 plus to A2 minus, that minus C2, etc. So that minus Cn, that from An plus epsilon goes to R here, and the S. Okay, right. So the gamma, you see, the gamma is a simple closed curve, a path. Okay, so gamma is a simple closed path. Okay, right. So and it is just a chain of this path. Okay, you can see you have that. So the principal value. Okay, the principal value is actually equal to so then becomes to be the limit of epsilon goes to 0 of mass infinity. So we can see that this is 1. Okay, and A minus epsilon f of x A1 dx plus A1 epsilon A2 minus epsilon f of x that's A minus 1 plus epsilon, and AN minus epsilon, AN plus epsilon to epsilon. All right. So this is the principal value we have. Okay. And the R in here, R is equal to minus 1 over epsilon. R is equal to 1 over epsilon. Okay. So we just do the limit. This is the principal value of that. When we have a finite number of simple poles on the real axis. Okay. So we have simple poles. Okay. All right. And so we can, so we have that, this is the limit. Epsilon goes to 0 of the line integral over the simple cross path f of z dz. Okay. And plus, okay. So now we have summation of I from 1 to n of the Ci fz dz, and the minus the x fz and dz. Okay. Okay. Because that but if we go on to that, okay, so the reason is that the line integral, okay, is equal to the line integral from plus minus 1 fz dz, okay, plus a1 plus to a2 minus epsilon, right, over the path, and plus minus c2 and the f of z dz, okay, plus plus c minus n fz dz plus an plus epsilon to r fz dz plus x of fz and dz. Okay, because that the R is the chain of this path. Okay, so by definition of the chain, you know, we have this one, and over this one corresponding to integral. So this line integral becomes to the corresponding real integrals here, okay, over a line segment, okay, over the line segment here. Okay, so we keep the line segment here and move all other parts go to the left hand side. Okay, so that these integrals becomes to the line integrals minus this line integral, minus this line integral, minus this line, minus this one. But the minus this integral becomes to the integral over C1. Okay, because the orientation is counterclockwise. Okay, so this is Cn. All right, so we have use sum of them and minus this one. Okay, and again, if we have proper, okay, so this goes to, in this part, for this one, if epsilon goes to 0, then this R becomes very big, all right? And so that the simple closed path gamma will enclose all the points, okay, in the upper plane, open upper plane. So this is 2 pi I, okay, summation. So of A is the pole in the upper half plane. Okay, in the upper half plane. Oh. Okay. In the upper half plane of and the residue of z equal to a of f of z. Okay, so the pole there, and plus pi I, all right, from the previous theorem, okay, as the epsilon goes to 0, so this is actually summation of A, the simple poles, the poles, okay, on the real axis, okay, and which are assume, we have assume simple, okay, of the residue z equal to a of f of z. Okay, so this is corresponding to this one. Let's go here, and this goes here, and oh, by the way, okay, I forgot to. All right, so provided that f of z is equal to this upper bound with limit of r goes to 0. And so this implies that the limit epsilon goes to 0 of the x equal to 0. Okay, as previous discussion. Okay, so we are able to evaluate the principal, the Cauchy principal values of an improper real integrals, such that the the integrand has singularity, okay, has a singularity on the real axis, okay. Right. Okay, so I think we have covered quite a few cases of evaluating real integrals by using the complex residue integration method. All right. Okay, so I have to stop here, and remember, next Thursday we will have the final examination.